welcome everyone. So we are now going into probability, and we'll be introducing the key results or the key facts that will span this topic, and then we'll be focusing primarily on conditional probability. But of course, once you're dealing with one aspect of probability, you have to bring in the entire family of related concepts. So when we talk about probability, what we're meaning is the likelihood of a certain event occurring. This, of course, is assuming that there's a range of possible outcomes, but those outcomes are not determined. So, for example, if we roll a die, we know that the range of possible outcomes is 1 through 6, assuming your ordinary die is what's in play. But we do not know which of those outcomes are likely to occur. And so if the die is fair or unbiased, then each outcome has an equal chance of occurring. And that's what we mean by random or fair. So in this presentation, what we will look at are we lay the groundwork for the videos that are going to come. So when we invoke certain concepts and certain formulae, you can come back to this video if you want a refresher. So here in result number 1, I've introduced the fact that probability of A is equal to NA over NS. What that means is that probability of A is equal to the number of elements in set A divided by the total number of elements in the sample size. So this would agree with what we understand probability to be in a relativistic term, in the sense of the probability is the number of successes over the number of trials, or the number of favorable events over the number of total possible events. And that is summarized as the number of elements in set A divided by the number of elements in the sample space. So the second result is a key result for us, that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. All right. Now diagrammatically, what number 2 tells us is the following. If we were to draw this as a Venn diagram, we have A and B there. So A union B is the entire shaded region. So we're including A, we're including B, and we're including the overlap. But in order to avoid a double counting of the overlap, we subtract the overlap once. In result number 3, we're told the condition for independent events. So events are independent if the probability of one event occurring does not influence the probability or the likelihood of another event occurring. So for example, if John and Mary are sitting a test, the probability that John passes the test will not influence the probability that Mary passes the test. Those outcomes or those events would be considered to be independent. All right. So if the results of one thing doesn't influence the results of another thing, we're likely to be observing independent events. And where events are independent, then the joint probability of them occurring, i.e. both of the events occurring simultaneously, is equal to the product of the individual probabilities. So the probability of A intersect B is equal to the probability of A times the probability of B. And that's also going to be a key formula for us. In number 4, if events are mutually exclusive, what that means is that if one event occurs, then the other cannot occur. So it's like night and day. So if you're in the same geographical location, it can't be night and day simultaneously. So if we were to graph this, what we would say is that the events do not overlap. So if the events do not overlap, they are mutually exclusive, and another word for them would be disjoint events. So mutually exclusive events or disjoint events, they don't overlap, and the condition for that is that the probability of A intersect B is equal to 0. Number 5 will be the formula for conditional probability. All right. So what conditional probability argues is, let's say that event B has occurred. What will be the probability of event A occurring given that event B has occurred? And the keywords, the buzzword to identify that we're dealing with conditional probability is that phrase given that. Now, there are some instances where the phrase given that is not used, and this is where conditional probability becomes a little bit more subtle, and you'll have to be able to read between the lines that this is a conditional probability questions. And as we work through some of the examples, hopefully we'll be able to illustrate those scenarios where conditional probability is being more subtly examined. So in terms of the diagrammatic equivalence, we have set A and we have set B, and we're arguing that B has occurred. So what we're trying to do is to look at this shaded region as a fraction of entire set B. So we're restricting our attention to just B, and we're looking at the overlap. That is a part of A, that's a part of B. So what is a fraction of A as a fraction of B? And then finally, the complementary event rule. So the complementary event rule states that the probability of A not occurring is equal to 1 minus the probability of A occurring. Another way of writing this rule is just to say that the probability of A plus the probability of not A will equal to 1. So this is a rule that will be invoked time and time again when we're looking at normal distribution. So it's really important for us to appreciate it. So the probability of A and the probability of not A must add up to 1. All right. So hopefully you will learn these and apply these, be able to apply these as we go through a host of examples that will cover particularly conditional probability, but will draw in a range of related probabilistic concepts. All right.